All right. So as I was saying, the previous lecture we just dealt with sort of the types of models and haven't even gotten to the mechanics of how you even fit models or what you can say about models. And so in this lecture we'll be going through one aspect of that, which is fitting models and what that means and various issues involved. All right, so first we need to think about what it means to fit a model. So the first concept, I guess, to start is goodness of fit. So remember, you might have a scatter plot. Again, just one variable predicting another, and you say you want to draw a line that fits the data. And so all that means is you want the line to go somewhere near your data points. A line is the model, and you kind of want your model to be meaningful, and you have data, so you kind of want the line to go near the data. And so this idea of goodness of fit can be quantified or formalized in a certain way, and we'll start off with the standard way of doing it, which is the idea of squared error. So let's just look through this slide. So we have our, so let's just start with the formula for squared error. So we just have a summation over all the data points that we have. So I is just an index that ranges from 1 through n. N is the number of data points. And we just have the difference between the data and the model. So d sub I is just the value of the ith data point. So imagine it's the y coordinate. We're normally predicting the y-axis from the x-axis, right? So the data is d sub I, and the model fit for the ith data point is m sub I. So you're just subtracting two numbers and squaring. And you do that for every single data point. So then you sum across all your data points. So there's not much going on. We're just taking the difference between your data and the model fit, and you're just squaring that and then summing. And the squaring means that deviations that are, if your model's too high or too low, it kind of doesn't matter for this metric because you're squaring. Squaring a positive number is positive, squaring a negative number is also positive. So let's go through a little depiction of that. So first let's look at the case of a high squared error. So error is bad, so high error means your model's a bad model. So our usual x versus y plot, and suppose these are our data points. Each dot you might think of a subject that has a certain x value and a certain y value, and you're trying to model these data. So in other words, let's assume we chose a linear model, say, a simple model, and we want to have that model fit the data or describe the data. So let's suppose this were our model. So this is just a line, right, that relates x. For every x value, there's a predicted y value. And if you really want to see the details, these are the actual parameters that describe this black line. So y equals 1/4 x minus 1/4. Let's just verify that. So suppose x is 0. Then that term goes away, and you're left with negative 1/4. So x is 0, and you go look at the y coordinate of the line. It's right there, which is exactly what it should be, negative 1/4. Okay, so this being the model, obviously it's not a great model of the data just because it's far away from the data. So let's be a little more formal. We need to look at the residuals, and the residuals are really just what we just saw here. So data minus the model. So if the data is greater than what the model fits, that's a positive quantity, right? So let's just look at this one data point. This data point has a y value of approximately 1. The model prediction is approximately 0.2. And so 1 is greater than 0.2, and it's specifically 0.8 greater than the model. So that's why this term would be positive. So this is a residual. It's kind of what your model doesn't explain. And I just drawn simple blue lines to indicate that differential, the difference between the data and the model. And so every data point has some residual. Maybe by chance you'll go through a data point exactly in which there is 0 residual, but almost all the data points will have some discrepancy. So all you do is measure that discrepancy. So just take data minus model, square it. So that just kind of rescales it a little bit, and then you just sum. So essentially squared error is just the sum of all these blue distances here. And so for this particular model, there's a lot of residuals. In other words, it doesn't fit the data that well. I mean, it's not totally out of the ballpark. It kind of gets near the data points near the bottom end down here, but it's pretty far away from a lot of the data points. All right, so let's go through a nicer case. So let's look at a case of where the squared error is lower. So in fact, we will use the exact same data set. These are exactly the same data points. And let's just look at, again, we're restricting ourselves thinking about linear models, and now let's look at this model. So this is a different line. The only thing that happened was I changed the parameters that describe the line. Remember, y equals ax plus b. So the slope is a little different, 1/2 here, and the offset is 0. And let's just check, right? So set x equals, I don't know, 1. So 1/2 times 1 is 1/2 plus 0 is 1/2. So if x is 1, the prediction of the model is 1/2 as expected here. Okay, good. So that's our new model. And in some sense, it's the same model, but we just changed the parameters. It's still a line. We just changed the parameters that define the line. And for this model, it clearly goes through the data points much better. And specifically, let's look at the residuals. So now I've drawn these little blue lines. It's kind of the difference, again, of the y coordinate of each data point relative to the prediction of the model. And as you can see, the total amount of blue lines here is much smaller than in this case. So, which is just another way to say that the squared error in this case is lower than in the first case. So the idea then is when we want to fit a linear model to these data, we're just sort of twiddling the parameters to make the total error small. And we've seen two simple examples of this setting of the parameters, 1/4 and -1/4, is a pretty bad setting, whereas if we changed it to 1/2 and 0, we'd get a much better model fit. All right, so this is pretty straightforward. Okay, so this was a simple case of one variable predicting another, and the reason we do that is because we can visualize it and kind of make some graphical sense of it. Of course, you can have 2 different regressors trying to predict the y, or 3, or 100, and you can definitely do that in terms of the mechanics and in terms of the code, but it'll be much harder to visualize. And so, but just keep in mind that all of this also applies to multi-dimensional or multivariate regression models. Okay, so we're going to take a little detour. Again, feel free to stop me if you have any questions, but if you don't, then maybe I'm explaining it extremely well. All right, so we're going to take a little detour and think about some geometric ideas. And it's technically not totally necessary, but I think there's some issues in regression modeling that can be addressed sort of in a geometric sense, and if they come up, we can go through them. For example, like what does it mean when regressors are correlated, or how does that sort of pan out? So I think this is useful, and so because we're introducing the idea of model fitting, we can kind of go over this geometric interpretation. So the idea then is we can visualize what we're doing when we fit a linear model in this kind of way. So if you remember this kind of matrix notation, so y equals xw plus n. So remember, y is a column vector with all the y values. X is this matrix, 2-dimensional matrix, where the regressors are in the columns, remember from previous lecture. W are the weights that we're trying to figure out, these sort of free parameters that we're trying to fit, and then n is all the residuals that we can't fit. Okay, so we're dealing with linear models, and because they're linear, we can write them in this fashion. And if you remember from last time, of the classes of models out there, we can sort of fit linearized models in this form, because in linearized models, you just take your existing regressors and do something like square them and then act like that's another regressor. But in the end, they all conform to this linear form, and you can write it as matrices like this. Okay, so I put here a 3-dimensional space because we can't visualize easily much more than 3. And the idea is the data we're trying to predict, so all of these y coordinates, in this case, we only have 3 subjects, and or 3 independent data points, and that's why my diagram has 3 dimensions. So it's sort of a horizontal is the first dimension, vertical is the second dimension, and through the screen is this 3rd dimension. And so if we observe 3, 4, 5 for the 3 data points that we're trying to model, that would just be a point in this space. So if you count 3 units on the first dimension, because the first data point is 3, and then 4 units on the second dimension, and then 5 units into the screen, oops, maybe you'll end up there. Of course, this is just a diagram, but imagine this data point line at the coordinate 3, 4, 5. Okay, so that data point's there, and we're trying to model these data, and we have this linear model. And so I'm going to start filling in what is the rest of this equation. So the X matrix is a matrix that consists of multiple columns, one column per regressor. And suppose one of the regressors, or one of the things we're using to explain our data, has the values 1, 1, 2. So that's just X sub 1, just referring to the first regressor, and we can think of that as a vector. So I just a vector, so the tail of the vector starts at the origin, and then it just points toward the point 1, 1, 2. So if you, again, imagine moving out 1 unit, moving up 1 unit, and moving into the screen 2 units. And so you have this vector that points at a certain direction, and I think I also have one other regressor just for fun. So some other variable that we're trying to explain y with, right? And that one, say, has 4, 0, 1. So we count 4 units, up 0, and then into the screen 1 unit. So we have these 2 regressors that we set up in this linear model, right? We're trying to model these data as a weighted sum of these 2 regressors, and the weights we don't know yet. The weights are these w's. So geometrically, what we're trying to do is use these 2 regressors to fit the data. And really all that means is we want to come close to the data. The data is out here, and we want to sort of use these regressors to get to those data. So what I've just done is sort of pictorialized, visualized the plane defined by these 2 regressors. So think of these regressors as little sticks, and those, since you only have 2 sticks, they perfectly define a nice plane yeah, question?
So would each regressor be like its own line or model thing? Or do they both form one?
Yeah, so in this model, that's a good question. This model, we have 2 regressors that we're trying to use jointly in one linear model. So our total model that we're using here is a weighted sum of the first one plus a weight times the first one, a weight times the second one, is trying to model the data. So notice that this is already more complicated than well, let me back up. So this example, our simple linear model explaining y in terms of x, there actually are 2 regressors, if you remember. There's the x that we started out with, and then there's also an implicit second regressor that consists of all 1s. So yeah, so in this simple example, there are 2 regressors, even though it doesn't seem like it. And then in this case, I guess I'm not making the second column all 1s, but the same ideas apply. So, okay. So each regressor gives some flexibility to the model to kind of get towards the data. In other words, fit the data. But we have 2 regressors. So in fact, combining both the regressors actually allows us to get to any point in the plane that these regressors define. Or another way to say it is the space they span, kind of a linear algebra term. And so it's a weighted sum of these 2 regressors, right? We can suppose we don't want any of regressor 2, so the weight on regressor 2 is 0, and we want 1 unit or one version of regressor 1. So that would correspond to the case W1 is 1, W2 is 0, and you multiply these 2 matrices, and all you've done is said that I'm going to allow x2 to have 0 influence, and I'm going to allow x1 to have 1 unit of influence. And so the model fit corresponding to a setting of 1, 0 would be exactly where my cursor is right here. So given these 2 regressors, one potential model fit is this point that is coincident with the tip of x1, and that's not that close to the data, so you wouldn't want that model fit. And so the green plane here is actually saying that with appropriate setting of the weights on x1, so you can scale this vector up, or you can actually make it go negative, and you can also add to it, since we're doing a weighted sum, you can sum some scaling of x2, so you can say I want 2 units of x2 or negative 2 units of x2. And so if we allow the weights to vary arbitrarily, positive or negative, any value, you can get any point in this green plane here. Notice the green plane doesn't subsume the data point, and we kind of want to get close to the data point. So what we do is get as close as possible. So this blue dot now is the point in this plane that's closest, and literally closest in terms of distance. You can see that is closest to the actual data as possible. And if we find that point, that's the optimal model fit. And optimal, again, just means you've minimized this quantity that we want to minimize squared error. And we've sort of assumed at the outset that we want to do that. So that's why we can now say that this point is optimal. And it's given, again, as I've been saying again and again, it's just a weighted sum of the existing regressors. You have a W1 and they have a W2. And I don't know what the actual numbers are 1.5 and 1. And you can kind of eyeball that. So 1.5 times x1 means take this vector and make it 50% longer, and then add to it 1 unit of regressor 2. So regressor 2 involves moving that way, so it's kind of starting here and then moving 1 unit that way. And then you get to the optimal model fit. Okay, so then we can fill in the rest of this equation, which is we didn't exactly fit the data all the way, so there's going to be some residuals, this n vector. And geometrically, the residuals are just sort of the distance. It's like what's left after the model did the best it could. So it's just the distance between the blue and red dots here. And notice I put this little perpendicular sign. Remember high school geometry or whatever? That these vectors are at right angles. Another way to say that is that the model and the residuals are now uncorrelated. We'll go through an example in 1 second to sort of clarify that. But so the residuals I denote with n, and then you can kind of fill in the residuals here, which is just the difference between the data, the y, and the model fit, which is this stuff given by in here. So the one contrasting case that's useful to look at is what happens at a non-optimal fit. So that's this next example. So here I just moved the blue point somewhere else on the plane, and that's a potential fit. There's some weighted sum of the regressors that can get you to that point, and then we can plot the residuals there. Notice the residuals are longer, which just means the squared error is larger. But notice that this fit, when you set the weights and you get that fit, these two vectors, so the vector that describes that fit, so this long dotted vector, and the residuals, they're no longer perpendicular to one another. And so the idea is when you've reached the optimal fit, it will be the case that your model fit vector is perpendicular to the residuals. And the logic is if they weren't perpendicular, then that kind of means that you can achieve a closer model fit by updating or changing one of the contributions of the regressors. Another way to say it is, what's the point in the green plane that's closest to this point? Well, you kind of draw a perpendicular line joining the plane and the data point, and that's kind of where this idea of perpendicularity or orthogonality comes from. That's just a synonym for perpendicular, I guess. All right. So again, the reason why I'm going through this geometric interpretation is you may find it useful for thinking about how regression works. And another motivation is it kind of leads to some sort of explanation for how we can do this kind of model fitting. So again, case of linear models, squared error, how do we actually compute the solution? In other words, what are the weights that achieve that solution? Question? Yes?
When my model is not optimal model, how do you know that whether my weights are wrong or whether I missed one of the regressors there in the model? So how do you know?
Yeah, so the question is, suppose you have a model and you have some setting of the weights, and how can you know if that setting of weights is not optimal? So I guess you could manually sort of change one of the weights and then compute the error and then see if the error goes up. So if you're at the optimal, in other words, the minimal error, then any change to the weights should make you do worse. So in other words, the error should go up. So depending on what kind of situation you're in, I mean, you could do that. You could just twiddle one of the weights and change it and check the error, and it should go up. And then no matter which way you twiddle it, so make it go bigger or make it go smaller, you should always, the error should always go up if you are indeed at the optimal point. Okay, so so if you have achieved the least squares solution, and it's also known as the ordinary least squares solution when we're talking about squared error and linear models. And so, as I said, the geometric interpretation allows us to see how you can get this solution. So what I just got done explaining in the previous slide was the idea that, and this is not really a mathematical formula yet, it's sort of an intuitive formula. The idea is if you have achieved the solutions, then the regressors, the dot product of the regressors and the residuals will be 0. So let me briefly go back to the previous slide. So we had said that this dotted line and the residuals are not orthogonal in this case. And also, you sort of related to that is each individual regressor and the residuals. So you kind of look at the direction of regressor 1 and the direction of the residuals. They're not perpendicular. They're somewhat pointing in the same direction. And similarly for regressor 2. Regressor 2 is sort of pointed in a similar direction as the residuals. Whereas if you are at the optimal fit, you look at this regressor and the residuals, and you kind of make them emanate from the same point. You can see that they're perpendicular. So if we have achieved the optimal fit, it will be the case that the regressors and the residuals will be perpendicular. And just to express that mathematically, it's just the dot product. So each regressor, take the dot product with the residuals. And so the dot product of two vectors is just you multiply pairwise elements and then sum. So if you take the dot product of each regressor and the residuals, it will be 0. And that's just a property of what it means to be perpendicular or uncorrelated. So if that's the case, then let's just expand that out a little bit. So again, we're not quite a mathematical formula, but we know what the residuals are. The residuals are just the data, which we know, and the model fit that we presumably have, the optimal model fit. And so that's just a redefinition of what are the residuals. And then finally, we can convert this to a real matrix formula here. And I'll leave it to you to sort of walk through to make sure that all of this makes sense. But just briefly, the regressors are, again, contained in the X matrix. And we want to compute the dot product of each regressor with the residuals of the model. So the residuals of the model is just the data. We already know what the data is. It's Y. That's easy. And the model fit is just the weighted sum of the regressors. So regressors times the weights. And here I have this little symbol. It means kind of an estimate of W, just to emphasize that of course, W is affected by noise, and with repeated experiments, we may get a slightly different answer. Anyway, it's the estimate of W according to sort of this ordinary least squares estimate. So anyway, that's just one gigantic symbol that stands for the weights that we're trying to find. And so all I've done is sort of replaced with real symbols what this equation kind of says. And you can sort of walk through it and prove to yourself that this equation formalizes the idea of taking the dot product of each regressor with the residuals. And so the idea is when we have that ordinary least squares solution, taking the dot products, all the dot products will be 0. And the reason that 0 is bolded is it's actually a vector of zeros. There's a 0 for every single regressor that we're computing the dot product of here. So, and then the rest of this is easy. You just expand through. So X transpose gets the Y and also comes over to this term, and you expand it out. Nothing crazy is happening, and then you can just solve for the least square solution. So you kind of move this term to the other side and then multiply both sides by the inverse of this matrix, which is some linear algebra, but it's just a set of algebraic operations. So what this is really saying is if you want the optimal set of weights, again, for a linear model, assuming squared error, then you can compute it just using some matrix operations based on your data, which is contained in Y, the values you're trying to predict, and in terms of the regressor matrix X. So there's a transpose operation. We can go over that when we do it in MATLAB, and there's also this inversion operation, which is kind of division. It's like a division of a matrix. So you kind of take the inverse of this big matrix, and then, but that's it. And then there's just another transpose. And so there's a series of simple matrix operations that you can do to compute the optimal weights for a linear regression problem. All right. So the linear models, I kind of foreshadowed this, I think, in the previous lecture, that linear models are nice because you can do this. You can write down a simple analytic formula in some sense that gives you the such that you can fit the model in like really quickly and simply. But then there's all these other models you could fit, nonlinear models that don't necessarily have this property, and so it gets slightly more complicated. So let's think about nonlinear models. So there's a way of thinking about this that involves the idea of an error surface. So in general, a model will have some number of parameters, right? The parameters in a linear model are just the weights. So you might have weight 1 and weight 2. So those are 2 parameters. And we're kind of trying to find, we're searching the space of potential parameter settings. So parameter 1 can be 0 or 1 or 2 or -1 or -2, and then parameter 2 can also be 0, 1, -2, etc. So there's this sort of space of potential solutions, and every point in the space has an associated badness, right, the error. And you're trying to find the one setting of weights that has the least error. So we can kind of think of that as a surface, and we'll do an example here. So, and that idea is general, like nowhere in that is necessarily tied to linear models. Linear models have weights, yeah, and they have error, that's fine. Nonlinear models also have that. Think of the nonlinear model like, well, we're going to do an example right here. They also have parameters, and you can also quantify residuals of a nonlinear model. So everything is, a lot of it is the same, this concept of minimizing error. So in this example, we again have a one-dimensional case just because it's easy to look at. So we have x and y, and we have independently measured subjects, say, and it's pretty, I mean, there's a very close relationship between x and y, right? But it's not perfectly linear. You can just see this by eye. And we could fit a line to it, but now we're dealing with the case of nonlinear models, so let's suppose we think this is a good model of the data. And so this, if you remember back in the previous lecture, this is what I call a parametric nonlinear model. It says, it makes strong constraints on what the relationship is. It says that I believe y is related to x through this kind of exponentiation operation. It doesn't have to be the case, but let's assume that I'm happy to start with this form of the model. So this is the model we want to fit. The parameters are a and n. So a could be a number. It's just a scalar. And n is a number. And other than that, we know y. Y is all the y coordinates of these data points. And we know x. And the goal here is we want to just fit this model to the data. In other words, determine the values of a and n that are appropriate for these data points. So that's what we're going to look at on this side. So just put up this massive figure here. Let's go through what this figure is. So we have 2 axes, essentially. There's n, which is just the exponent parameter. And there's also a, which is call it the gain parameter. And we have, I judiciously selected a couple values to show you of each, for each parameter. Of course, the potential values that these can take can extend beyond this. N could be greater than 4 maybe, and a can go to 100. And I'm just showing you part of the space, but we're trying to visualize the parameter space here. And so at each combination of a and n, I have evaluated for you. I haven't shown you, I mean, we can go through the MATLAB code that does this, but I have taken specific values of a and n and substituted them in here and computed the residuals. So I've computed the model fit and then subtracted the data point and squared and summed. And that gives us a single number that we're using color to visualize. So this is squared error where there's a certain range, and dark is good and light is bad. Light means high error and dark means low error. And so we can visualize all the different squared error values using this kind of image, which is cool. And just so that you can see intuitively what this would be like if we were actually look at it in sort of 3D. There's this kind of surface. There's this curved surface that has edges that are kind of high, and then the surface kind of dips down at certain values, and you can kind of see that here. So we've just taken A and N and kind of used this used height above this plane to visualize the surface. But it's the same data. It's the same set of values that we're kind of looking at. But that might help you, give you some intuition. Okay, so the name of the game is we just want to find the setting of A and N that is the minimum of this surface. This is the idea of the error surface. We're looking at error, and we can think of all the potential parameter settings as kind of mapping out a surface. So how do we find, so I'm pointing to the minimum because I can see it, but how do you actually find that minimum? So we're going to use this idea of a local iterative optimization approach, and we're going to step through that. So imagine, so I've just plotted here I've taken one point in this space, so I've started at sort of the bottom left. When A is 0 and N is 1, let's just look at what that is. So A is 0, so we have y equals 0 times x to the 1 power, because N is 1. Well, 0 times anything is 0, so really the model is y equals 0. And lo and behold, we plot that model, it looks like this. So y is always 0. So this gray line is one potential model fit according to this model. And it's a very bad one, as you can see. It doesn't get close to hardly any of the data points. But it is a model, it's fine, and so that corresponds to exactly this part of the space. So we call that the initial seed, because in this type of approach, we're going to start somewhere. You gotta, so it's your initial starting point. And the seed kind of means you put a seed into the algorithm and let it grow or something. Anyway, we're going to start at that point in this parameter space. And then all we're going to do is look around us, sort of in the neighborhood of this initial seed. We're going to poke around and see which direction will allow us to decrease our error. So as you can see, if we move to the right, the error is pretty much the same. It's all white colored here, so that's not going to help us. Whereas if we move up, we get into yellow. That's good, because we're decreasing the error here. So we might imagine after we iterate a couple times, so iterate just means you do it once and you do it again and again, we might find this kind of path. So we might move there and then move there, move there, move there, move there. And if we now visualize what's happening, so let's look at this data point. Or sorry, not data point, this step in the process. So that's when A is 3 and N is 1. Let's look at what the model fit is for that. So A is 3, so y equals 3x to the, again, we're still at N equals 1. So y equals 3x. So that model fit is given by this dark line here. And you can kind of convince yourself y equals 3x, so x is 1, y should be 3. So we look at 1, 3. That's exactly right. So given this model fit, that's pretty good. Not totally right, but it's much better than where we started. All right, and you can imagine what happens next. We kind of keep going, iterate, iterate, iterate. We're moving closer and closer to the best point in this space. And so let's look at that point. So at the value of a equals 5, and when n is 2, so the model is y equals 5x to the second power. So y equals 5x squared. And I plotted in black exactly that model. So let's just check it. When x is 1, so we're saying y equals 5 times 1 to the squaring, which is just 5. So x is 1, y should be 5, exactly there. Good. So given this model in black, and notice now it's fitting the data quite well. All the y residuals are, I mean, there are residuals. So I didn't draw the little blue lines for you, but there is some discrepancy between the y value and where the model fit is, but it's much better than these previous models. And so this little point is the point in the parameter space that we're looking for. And you can kind of think of where that point is on this 3D diagram. It's kind of at the bottom here where my cursor is. So that's really all that's happening. We're finding in the space the optimal point. That is the point that minimizes this error metric. Any questions about this?
There is more than two optimal.
So in this case, there is only. Actually, I don't know. There might be more than one optimal. Actually, we're going to get to that issue in a second, but that's definitely an important worry and something to worry about, I guess, is if there's more than one solution, and we'll go over that in a second. I think for this example, at least in the range of values I've shown you, there's probably only one minimum here. I don't know. Did you see another one? I can't tell by eye, but. So in the lecture notes, I won't go over this, but I gave a little example of more of the mechanics of how this works. So to do this kind of procedure where we start from the initial seed and kind of follow this path, there are different ways, different algorithms that differ how they go down this path. And I give an example in the lecture notes of a specific case. So if you have a linear model, and again, minimizing squared error, then you can compute easily what's called the gradient of the error surface. So this is, again, a surface, right? And the gradient is just the derivative of this surface with respect to the parameters. So you can ask, if I'm at the initial seed and I want the derivative of the surface, let's only look in the direction, this horizontal direction. So remember, derivative is just like in calculus, kind of the slope of the function. So you can look at the slope along this direction. And if I were to increment n by a little bit, so it's like rise over run, that's kind of what slope is. So if you increment n, that's sort of the run, or the x, the delta x, your error surface isn't changing much at all. So the derivative, if you're at this point with respect to n, should be very small, maybe 0. That kind of says the error surface will change by a very small amount, maybe 0, if you change n. Whereas if you compute the derivative in the vertical direction, if you increment this vertical direction a by a bit, you see that the error drops dramatically. So it goes from white to yellow, which is kind of like 550 to 400. So the derivative of this surface in that direction will be a large negative number, or very negative number, meaning that your error function is going to go steeply negative if you do increment a little bit along this direction. So I go through this example that you can read in the lecture notes of how you can compute that for a specific case of a linear model. And given that we can compute this idea of a gradient, so the gradient is just the derivative in each direction considered separately, we can then use that to kind of guide us in this path. We can kind of figure out which path to go if we know something about the gradient of the error surface, or the error function here. Excuse me. And when we go through some MATLAB examples, we'll actually implement that and play with it and kind of get comfortable thinking about how you might actually handle the gradient and optimize this error surface here, or optimize or find the optimal solution. All right, any questions? So this idea of multiple solutions is exactly next slide. So there's an important distinction between linear models and nonlinear models with respect to this problem of, it's called local minima. So let's first go through these examples and then reflect upon what it means. Okay, so abstractly, remember we have this parameter space. And in this case, I only plot one parameter. Of course, your linear model may have 100 parameters, but the same intuitions apply. So we have this parameter that can take on many different values, and we have this error function. And if you have a linear model, it's always going to be the case that the shape of this error function will be, the technical term is convex, which basically means it's kind of always a bowl. There's not going to be bumps in the surface. There's always going to be a nicely well-behaved bowl, which means that if you find a point that is a local minimum, so local minimum just means locally, which means nearby that point, it is the minimum of the error surface. So if you find a point that is indeed a local minimum, so if you look at this red dot, anywhere you move around, up or down on the parameter, you do worse. So it is a local minima. But in the case of linear models, you're guaranteed that that minimum is the global minimum. It is the optimal solution. And so in nonlinear models, that's not the case. So let's just look at a little toy diagram of that case. So in a nonlinear model, again, it has parameters, and the setup is identical, where we have an error surface that we're trying to minimize. It might look like that. So now we have multiple bumps, and that's a problem, because if we land in this bump, we're at a local minimum, so nearby, that is the best point. But there's this other point here, which is also a local minimum, because nearby it is a minimum, but it is really the answer we're looking for. It's the global minimum. So of all the possible parameter settings, this is actually the fitting the data the best. And so we want this global minimum. We don't really want this local minimum. And the fact that there are multiple local minima, that presents some problems to us. So to deal with the issue of local minima, I mean, there are lots of different strategies. Some general strategies might be like this. So one strategy is, suppose this is your error surface, and suppose we are using this kind of local iterative approach. So you have to start somewhere, and you kind of go down the error surface to a potential solution. So assuming that's our strategy, one idea for avoiding local minima is just start at many different spots. So you might start where my cursor is, so you pick parameter value to equal this here, and then you're here on the error surface, and then you kind of go down and down and down and stop, and then you find a potential solution. You don't know if that's the best. So to guard against that, you could start at some other point in the space. So start at this value of this parameter, so start here. And if you descend and descend and descend and get to the minimum, and then you compare, oh, am I doing better than I did before? I am. So let's throw away that solution, actually stick with this one. So one strategy then is you start at many different points in the parameter space and just optimize each point and kind of pick the best that you have observed. The disadvantage, of course, is computational time. So if each time you do it takes a second, you can get away with trying maybe 20 or 30 or 100, but at some point it starts getting intractable. Like if your parameter space is 10 parameters, then you choose 3 different starting points for each of the 10 parameters. That's 3 to the 10th, and that's a big number already. So another strategy is brute force. So you could just say, I'm going to try setting the parameter to 1 and 2 and 3 and 4 and sort of try many values and not optimize each one. So the optimization process, of course, takes time. So if you have to increment and decrease and blah, blah, blah. But what you could do is just grid your parameters up and just evaluate your model at many different parameter values and kind of check over the range that you've gridded, which one is the best. And that's kind of another approach. I guess the lesson, I guess, at the end of any of this, especially when you have potential local minima, is really to look at your data and your model fit. So you can, assuming your data aren't horribly noisy and that there's actually an effect to model that you can see by eye, then it's always a good idea to make sure that your model hasn't converged to some fit that's just way off, right? And only you can sort of visualize your data and realize that. The code, it's hard to get a piece of code to automatically realize that. All right, any questions on this so far? All right, so broadly speaking, we're kind of done in terms of model fitting, but there are still some loose ends. One loose end is, why did we start off saying squared error? I just kind of told you up front that, well, we're trying to fit a line to these data points. So let's say we want to minimize the difference between the data and the model, and then take that and square it and then sum across all the data points. But one question is, why did we do that? What's the motivation? So this revisits some probability theory back in the first lecture, so let's refresh our memory. So this was our favorite little distribution, our Gaussian distribution. Remember, this is a univariate, so there's one random variable here, x, and then for each potential setting of x, we have some associated probability or likelihood. So what we can do is, there's two things, I guess. One is we know what distribution we're using, and we can ask how likely is any particular value of x. So this is the normal distribution, mean 0, standard deviation 1, and we can ask if we observe, if we're talking about a value of 4 for x, we can say that's very unlikely given this distribution, which just means the height on this function is very low. There's a very small probability of observing values out here, all right? So that's pretty straightforward. Now, we can reverse that and think, given a set of data points, what specific Gaussian distribution will make those data likely? It's kind of reversing the question. Here, we fixed the distribution and ask the likelihood of some data points. But let's say we're not going to fix the distribution. We're just going to look at the data points. We're going to ask, where should I put my Gaussian to kind of make those data points likely? So here's, just revisit the previous slide, think about this. So just ignore everything else on this slide except for the data points here. So we have a bunch of observations of this one thing we're measuring. And you can look at all these data points and kind of visualize, maybe I should make a slide that shows this, but there are many different Gaussian distributions. They have different means, they have different spreads, and you can kind of think, suppose my Gaussian was centered at 3. Suppose there was a Gaussian distribution out there. All of these data points would be extremely unlikely. So that's a very sort of unlikely choice for the Gaussian distribution that might describe these data. Whereas if I move that Gaussian to be centered on 0, then these data become much more likely. And then analogously for the spread. So if the Gaussian distribution were centered on 0 but were really skinny, then that's still, all of these data points out in the tails here would be extremely unlikely. So there's going to be some optimal mean and standard deviation of the Gaussian that kind of makes all of these data points likely. So why am I telling you this? Well, this will help us understand where squared error comes from, and hopefully that gives you a better understanding of model fitting in general. Okay, so just stepping back 1 second, sorry. The idea that we're going to choose the Gaussian that maximizes the likelihood of all of these data points, it's called maximum likelihood estimation. So maximize the likelihood of your data estimation. And we're gonna apply that to our regression case. So let's kind of transition from the simple one-dimensional variable case to the case of fitting data. So let's revisit our simple linear model. Let's back this direction. Aha. So okay, so let's focus our attention on this scenario here. So we have a bunch of data points. We're fitting a line, and this, on the right-hand side at least, I have actually fit the line, so you notice that it goes through the data pretty well. So we're going to assume here that these data points, so namely the y values, we're focusing on the y, that these data points are distributed Gaussianly, Gaussian distributed. And what that means is, let's just focus on one particular point in this plot. So look at when x is 1. So when x is 1, let's talk about this one data point right here. So this one data point, our model isn't exactly fitting perfectly. There's some residual. But the assumption here is that the spread of data points around my line is described by a Gaussian. So in other words, it's kind of like noise. So maybe the true model is the line here. It's just due to whatever variability, so it kind of depends on what you're measuring and where that source of variability comes from, but the variability around the line we're going to assume is Gaussian. So in this particular subject, the idea is there's some unknown variability that caused that subject to be, about 0.3 higher than my predicted model fit here, right? So that subject has some residual. That's fine. We don't know where that comes from, and we're going to assume that variability, suppose we were to measure that subject again, or some analogous subject, that we might then find maybe the point to be below our line. And so there's going to be variability around this line, and we're going to assume, just for this example here, that it's described by a Gaussian. So on average, the mean of the Gaussian will be 0. So on average, we expect the data points to be on exactly our model fit, but there may be some variability due to whatever. And that variability will specifically we'll assume to be described by a Gaussian. There are many other probability distributions, right? But the Gaussian is easy and tractable, so let's assume it's Gaussian. And furthermore, let's assume all of the data points will be equally described by that idea. So you go look at x equals 0 and look at this data point. In this case, this data point is below our model. And we'll assume that it's the same Gaussian variability distribution that's describing the variability of all of these data points. Okay, so technically the idea is independent, identically distributed. So what does that mean? Identically distributed means the noise for this data point is coming from a distribution that's the same for this data point, the same distribution for this data point, and all the data points. So all the data points are identically distributed in terms of their noise. And then the other part of that is independent. That just means the noise for one data point is completely unrelated to the noise for the other data point. Essentially, we sort of went briefly over this, the idea of independence, in a previous lecture. So if we were willing to make all of these assumptions, that the variable is Gaussian and it's independent across data points and it's the same Gaussian, like the same spread is describing all of these data points, then we can start making headway on this idea of where does squared error come from. So let's get to that. Sorry. Okay. And the upshot of all of this will be this title, but we'll get to there. We'll get to how that actually comes about. So I think it's useful to try to go through this symbolism here in the math derivation. And hopefully I can explain it in sort of straightforward fashion. So we're quantifying the likelihood of our data. So D stands for data, and this bar just means given. So the likelihood of our data given some model. And the idea is we don't know what model to choose. That's kind of the fitting of the model. We don't know what setting of the parameters is optimal, but that's where we're trying to derive here. So just like in the case of our one-dimensional Gaussian, right, we're trying to maximize the likelihood of all of these data points given some Gaussian that might move around and get fatter or skinnier. We're going to do exactly that here, but in the case of our model. So we can write the likelihood of all our data points using just the symbol. So this big pi sign is just a product. So what's the likelihood of flipping heads once and flipping heads twice? The first time is 1/2 probability, the second time is 1/2, and you just multiply. So there's a 1/4 chance of getting heads. So probabilities can be multiplied, and this is where that assumption of independence comes from. Anyway, we can say the likelihood of our data points is just the product of all the individual data points. This is likelihood. So I ranges from 1 through the number of data points. D sub I is the ith data point, and P is just probability. So I'm just rewriting what we kind of said in words here. So it's just the product of all of these probabilities. And here's where all the magic happens. Because we were willing to make all these assumptions about Gaussian distributions, we can just write the probability as, remember this was the formula for the Gaussian. It's just some normalization constant stuff and some exponential that's kind of has the sort of the squared stuff. So actually, yeah, let's just make sure we know all the terms, right? So the Gaussian has a certain spread, that's the sigma. Pi is a constant, no big deal. E is a constant. Sigma, again, is just the spread of this Gaussian, which we don't know, of course, yet. And D sub I is the ith data point, and M sub I is the model fit at that data point. So let's just link it back to this, our figure. Oh, I can scroll using my fingers. So all that's doing is saying, for each data point, we're just computing this residual. So we're asking, what's the probability of this data point under our noise model? Our noise model is a Gaussian. So if there were a Gaussian with a certain spread, I can calculate how likely that data point is given that I have the model fit. So it's really just putting that one-dimensional this case sort of on its side, and now we're sort of computing the likelihoods of the y values of these data points given our noise model. So moving back to our equation, right? So d sub I minus m sub I is just the residual. It's just those blue lines. And we're just asking how likely is that deviation? How likely is that blue line residual under our noise model? So hopefully that at least makes half sense. But once you get that, then the rest is just mechanics of churning it through. So let me just quickly go through that. So once we have, the logic is we can write down now the likelihood of our data. And what we want to do is maximize the likelihood, right? Just like in our one-dimensional case. If we know how to calculate the likelihoods of all of these points, then we will know how to shift our Gaussian. We're just going to move the Gaussian around and make it a certain size such that the likelihood of these data points is maximized. And that's exactly what we're going to do here. So let's ask what model, so M is just standing in for the model, what model will maximize this thing in the parentheses? So this is argmax. So it's kind of like, tell me the M that will maximize this quantity. For convenience, so there are a bunch of mathematical tricks going on here. So if you want to maximize this thing, it's equivalent to maximizing the log of that thing. Log kind of preserves, log is a function that's monotonic, so it's not going to change anything about what will maximize it. So, and we'll do this just for mathematical convenience. And then we can equivalently say what model will minimize the negative of this thing in the middle. The thing that maximizes x will also be the thing that minimizes negative x. Big deal. So then we're almost done. So we wrote down up here this term that is the likelihood. So we can just say, substitute that in and just put negative log likelihood. So I've just rewritten that thing in this little parentheses. And then just do a couple simplifications. So log of a product is just the sum of the log of each of the individual terms, and you can, if you care, walk through this and just make sure I'm doing everything right. And so you can just simplify. And then there is one interesting thing. So remember, the big picture is this shows us if we want to maximize the likelihood of the data, choose the model that minimizes this big gigantic thing. Well, notice that this term, so this is log of 1 over sigma blah blah blah, this term doesn't have m in it. So this term doesn't matter at all to finding the optimal model. So you can just delete that term. Okay, that's all I've done. So I've thrown out that term. Things are getting simpler now. So this is saying our answer will be the model that minimizes this kind of term. Well, notice that sigma, so sigma describes the spread of this noise model that we're presumably describes the data. Sigma has nothing to do with the model choice. So we can kind of get rid of the sigma also. So in other words, it doesn't matter what the spread of our noise Gaussian was. We'll get the same answer regardless. So for simplicity, let's just ignore it. So throw it away. It's getting even simpler. Now we see that we have what is, our answer will be the model, the M, that minimizes this thing in the middle. That should look familiar. That's just the sum of all the residuals squared, or sum of all the squared residuals. And so we can just say squared error. So this exercise was just trying to motivate and maybe give you some connection between probability theory and model fitting here. It's just supposed to show that if you make certain assumptions about the noise and then write out the likelihood and then say that I want the model that maximizes the likelihood, you can just churn it through and then realize that, well, the thing that maximizes the likelihood is the model, or the model that maximizes the likelihood is the model that minimizes the squared error, which is where we started this whole lecture from. So that makes life easier. Right? Squared error is easy. You just subtract sum and squared. And this is a lot harder. But so it's nice that we sort of end up with something easy. But there's a close connection between why you would want to do that. Well, you would want to do that if you, again, assume Gaussian noise and say that you want to maximize the likelihood, et cetera, et cetera. All right. So now we have some idea of where squared error comes from. But notice, remember we started the class with like just thinking about distributions, and yeah, the mean is fine if your data is Gaussian, but what if your data is not Gaussian? Then that's why you might want to use robust things like the median and all these sort of non-parametric things that follow. So in the context of model fitting, all of this entire slide was in the context of assuming Gaussian noise, but what if the noise is not Gaussian? So there are some alternative things. So if you do have a nice parametric form for the noise, you can kind of work through, maybe it's not squared error you're minimizing, maybe you have to minimize something else. But let's think more generally about the error metric. So one example, so this is an example, I like to lead through examples. So again, one-dimensional data, X is trying to predict Y, and suppose you observe these data points. So these data are quite weird looking. Scatter plots are very useful for that. Let's say I'm fitting a line, and specifically I'm fitting a line and I'm going to minimize the squared error as usual. That in black is the optimal fit. I've done it actually, and this is what the result is. And so I mean it's useful. It kind of shows what we kind of see, that there's a positive relationship, and you know it kind of goes near the data points, but you could argue that this is not the greatest model. So just to refresh you, that the metric we're using here is minimize the sum of all the squares of all the residuals. Fine. So suppose I showed you a different linear model. So we're keeping the model the same. We're not changing the model. We're just changing the parameters. And suppose I show you that line. So there's a gray line here that arguably is a much better summary of the data than the black line. The idea, you could say, is like maybe these subjects were well, there's this term outliers. The definition of outliers is a little complicated or unclear, but let's just say we want to ignore these subjects for whatever reason. Then if that were the case, then the gray line is a much better summary. Like it actually goes reasonably close to a lot of the subjects down here, whereas the black line isn't that great for a couple of subjects, but most subjects the black line is pretty far from. So this gray line I just drew, but I actually fit it according to a different criterion. So this criterion is just the absolute error. So it's almost the same as squared error. The only difference is we're not squaring the residuals. We're just taking the absolute value. So we are converting positive and negative to both positive, that's for sure, but we're not additionally squaring. So squaring you can think of as kind of accentuating really big values. So if you have 2 and you square it, becomes 4, no big deal. But if you have 10, it becomes 100. And so you can think that these y values that are way out there, so this guy's almost 30, and you square the residual corresponding to that data point, it's going to have a huge influence on the overall error that you're fitting here. Whereas if you only take the absolute value, I mean, this guy will still have an influence. It will influence by roughly 30, but it won't be 900. So if you just change the error metric, we get a different optimal linear fit here, as shown by the gray line. And so, I mean, this gives us enormous flexibility, and that may be annoying. Like, yeah, there is a motivation for squared error, fine, Gaussian noise, but I mean, if you look at these data, these are highly non-Gaussian. And so the question then is, what can we use instead? And you can just choose. I mean, it's almost no less arbitrary than squared error. You can choose absolute error, and you can fit that model. And I like the gray line as a summary of these data. So the absolute error actually can be motivated in a similar way that the squared error. So squared error corresponds to this Gaussian assumption that we just went over. Absolute error also actually corresponds to assumption. It's an assumption of Laplacian noise. So there's like Gaussian, and then there's this other term, Laplacian. And the Laplacian is almost just like the Gaussian, except, so remember the formula for the Gaussian, it looks kind of like that. So the Laplacian just takes away the squaring and essentially puts its absolute value there. So you can, so it's almost the same, just you're changing the exponent. But you do get quite different results because they kind of make different claims about the noise. And in fact, there's this cool connection between squared error and absolute error and kind of things we've already seen in the first lecture. So if you have a set of data points, I guess I'll go back to this slide. Just think about one variable. You have all these data points, and what value is the value that minimizes the squared error of these data points? So just the differential between the value in each of these numbers. So for example, if you chose -2, if that is the quantity you think is the answer, then there's a lot of squared error. So the differential between -2 and these is small, but there's a lot of differential between -2 and all these data points. So -2 is not the answer. So what value is the value that minimizes all of these squared deviations from each of our data points? It turns out that value is exactly just the mean of all the data, which isn't totally obvious why that would be the case. So then let's think about this absolute error idea. So what value, given these data points, is the value that minimizes the sum of all the just distances? We're not squaring, sum of all the distances to all our data points. It turns out that value is the median. Again, not obvious why that would be the case. But this shows you there's a nice parallel between this idea of we want to use non-parametric or robust summaries of data and this idea that we might want to not just minimize squared error, which is kind of the typical and default, but maybe we want to minimize the absolute error because that's kind of a more robust way to describe or summarize our data. And in fact, you can do this. I mean, we'll do this next week when we start looking at MATLAB examples, but you yourself can write code or whatever to fit a model that minimizes absolute error. And in fact, I've done things like this for my own work. You don't have to use squared error. You can use whatever error metric you like.